So, we are going for the next problem, and here the problem is that again we take a ECG signal sampled at much higher frequency, that is 1 kilohertz, and this signal, as the name suggests, ECG underscore HFN dot dat, the name suggests itself that it is corrupted with high frequency noise. So, we have to perform synchronized averaging. So, for that we have to select the QRS complex from the signal, and we need that what is the span of one cycle first for the purpose of taking that period for averaging, and also the QRS complex will help us, or the bit location will help us to align actually those cycles. So, we need to perform that exercise, and to find out the bit we are asked to use correlation for that, and we are also asked that we should be careful that it should not be part of the cycle, it should take a full cycle, and with respect to that noisy signal, if we put that, then we can appreciate that what is the change it brings. Next is that as we continue, select the QRS complex from a different bit for use as a template and repeat this experiment. Okay. Observe the results when the threshold on cross correlation function is low, that is 0.4 or high, and comment. That means, after taking the cross correlation, the bit location is actually find out by taking actually a threshold, that where the correlation is high. Now, how high is to be taken as high, that is the question we are asking, and if we change that threshold, how that will impact the result. Okay. So, that is the second part. Next is that find the signal to noise ratio of the above case, considering the best output as the reference signal. Okay. So, it is like the previous one. Now, let us look at that how to get the data, that here the link is given, that how we can get the signal and the data file, it is given here, okay, and the corresponding that MATLAB file is also given here .mat, okay, and again we need to keep in mind that we should put both the data and the code in the same file, okay, or in the working directory we can say directly. So, we know these things from the previous experiment, and from there we proceed. Now, what is the motivation to go for the synchronous averaging? Let us look at that. We know the linear filtering, it cannot work well that when the signal and the noise spectra they have overlaps. If the signal or noise they are separated or have a very small overlap. For example, if we take the power frequency noise, it is concentrated on a particular frequency. So, what we can do, if we can just eliminate all the strength at that particular frequency, we eliminate the noise completely. By that, we sacrifice some part of the signal strength also at that particular frequency, but using a filter like notch filter, we minimize that loss. That means one particular frequency only we are losing that signal strength, and if we can sacrifice that, we can get rid of that. But when that is actually spread over a band and both the signal and noise have common actually spread of or common range of frequencies, then if we try to eliminate all the frequencies, then we have a big loss in terms of the signal also. So, in that case synchronized averaging could be a better way, and it is specially successful when the noise is random with 0 mean, and it has to be uncorrelated with the signal, and signal has to be stationary or periodic or at least quasi periodic, and in this case our signal ECG is a quasi periodic signal. So, we can go for that synchronized averaging or synchronized averaging. So, first we look at the signal corrupted with high frequency noise. So, here is the code for that we load the signal that here in the variable x, sampling frequency is given 1000. So, we assign the variable fs, calculate the number of samples in the data, that is using the command length, and then we prepare the time axis, that is first we write that a ramp that it is increasing in terms of the sample number 1 to L and multiply with 1 by fs, that is giving us that sampling interval, and at the end of it we issue the figure command to create the pen and plot using the command plot t comma x. So, here we see the signal, it is having the same span between 8 to 9 second, we have the signal and the amplitude is in negative side, maybe that minus 2.5 or even more than that, and above also it is about 2.5. So, it is limited within that span. Okay. So, we have the signal now. So, next job is to find out that the template and look at it. So, here we have extracted one cycle manually, one cardiac cycle, and for that what we have done? We have done few visual actually examination, and we have taken a starting point for selecting the template, that temp start. We have taken that point, that starting point as 950, okay, that is manually selected. Again the duration is also manually selected. We have taken that as 801, that we have taken a odd number to make the window or the duration that odd, and that we have assigned it to a variable that L underscore temp. So, that gives the duration of the template. So, the template now it is copied there, the variable or the vector template, that which will keep that part of the signal x starting point from temp underscore start, that is the starting point, and till the end point of the duration. Okay. And then we can actually plot that signal. Now, we create that time axis, that is T1 having the length that L underscore temp, and for this ramp we are again multiplying with 1 by fs to get the time axis, and using the figure command we have created a new pen and we have used the plot command to plot it here. Okay. And let us see that what is the output. Here we get the output. Now, we can appreciate the high frequency noise much better. There is a good amount of noise, but this is good enough to see that not only that what is the amount of noise, that in the ECG signal the most of the energy of the signal is concentrated near the QRS complex, and rest of it is there in P and T. In between the T, that means end of T to the beginning of P, in between there is supposed to be isoelectric line or no electrical activity. So, whatever is there is noise. So, if we take a template, even if not as long as one cycle, if we just capture that P, Q, R, S and T, that is good enough for this purpose of finding out the location of the bit, and that is the fact we have used here. Okay. Otherwise, technically speaking, we should have taken a little more, but increasing that we take some more samples which have more of noise. So, that does not add much value. Okay. So, now let us proceed. For the cross correlation, what we do? So, first again we recall that Fs is our sampling frequency here, then length of the signal is L, we recall those things, then time axis is T, we know all of them. Now, we come to a new thing, that when we are computing that correlation, actually we need to understand that what we have the variable x, it has a duration. Okay. So, this may be the data length starting from 1 to L. We have taken a template. So, template is having some length smaller than the x, but it has some length. Now, the middle of it we take as the center of it, we have taken as the index of that template, and we just slide this template from the beginning to the end. Okay. Now, in that way, what we have to do, every position we need to take the dot product of the signal and the template and sum them up to calculate the correlation. Now, for the part that when we are at the first part, this portion actually that we have to take the multiplication and there is no value, in fact, nothing is assigned there. So, if we try to compute it, it will throw up error because x is not defined. Same way, when we go to the other end beyond L, when it will look for actually the values to multiply, again we have the same problem. So, we need to pad actually the signal x from both the sides, and the padding should be almost half of the length of the template. That means, actually this part, that what would be outside when we start at the beginning, or what would be outside when we go for at the end. Okay. So, how we get that length? We can simply divide the template length by 2. So, that is what we have done here, and we have taken the floor function because it is a odd number. How many samples would be extra? It cannot be fraction. So, it would be just the lower integer. So, we have taken the floor function to get that, and next we have created the padded variable x 1, where at the beginning we have the zeros and at the end also we have zeros. And here one small thing just to note, that we have taken the x is a column vector, and so we have taken these things also are that column vectors. So, they are adding up in this way, okay, and the resultant is also a column vector. Now, the length of it is actually the length of the signal x plus length of the template minus 1. Okay. How we are getting minus 1? Because we have taken the floor operation here. Okay. So, that is how we get, and if you recall your books, then you would recall that if I take the correlation of two signal, one is of length A, another is of length B, that the number of terms we get A plus B minus 1. Okay. So, that much here we have to create the length of the padded vector. Okay. That is what we have done, but we are interested only the correlation value of the A points, and we will just keep track of that. Okay. So, now in this loop we are just doing that. For the length of the signal x, we are computing that. So, we are taking the first the product, that is dot product of the template and the signal, and for the dot product please look at that symbol dot into star. Okay. So, if you have given star, it would have been multiplication of two vectors. So, we need to check the dimensionality, that whether that we can take the product in a meaningful way, but as long as the length of the two matches, we can take the point wise product, and we need not have to bother about that whether the dimensionality, that means that number of rows and number of columns, they are in agreement or not. Okay. Only the length should be same, that is good enough. Okay. So, that is the symbol for the dot product. Next what we do, we normalize that thing, that we need to take the sum of the these all the product terms and normalize it with the energy of the template and energy of the signal of that portion. Okay. Now, what the norm is doing? It is actually calculating the L2 norm. So, what it is doing? It is first taking the, we can say again the dot product of the signal, that means temp dot star temp, then we take the sum of it and then we take the square root of it and we get the norm temp. Okay. The same thing we are doing for that segment of the signal of the length, that we are of the same length as the template. Okay. So, that is how we get the energy, and we are dividing or normalizing with that the energy, or the I would say that rather standard deviation or square root of energy of the template and the signal at that portion. The reason is that here that the sum of product, otherwise it would be affected by the scaling of the signal or the template. So, to make it invariant, we should take that normalization, and instead of correlation we are getting correlation coefficient in that way. That will help us to judge that whether the correlation is high or low. Otherwise, any scaling of the template would actually change the correlation values. So, we simply want to actually eliminate that problem and make it scale invariant. Now, here we find that the correlation between the template and the ECG signal. Okay. So, for that we are showing that the input and the cross correlation. So, first we have taken the figure, then again use the subplot command. The intention is to divide the pen into two parts, that is two strips of rows. Okay, like this, the full image is divided into two parts. The top part we are plotting the signal, that is plot that T x in the first one, and the second one is plotting the cross correlation or correlation coefficient. Okay. So, here we get that it looks like very similar to the ECG signal itself. The cross correlation signal or the cross correlation coefficient is very near to the ECG signal. Only thing, because we have normalized, the values are between 0 to 1, and apart from the QRS complex there are some undulations. So, what actually we can infer from that maximum match is there when it is matching with the QRS complex, because maximum energy is present there, and the moment it gets deserted there is a sudden change, and that gives rise to high value of that correlation at some point, which gives rise to some feeling that we have got the R wave back. Okay. However, when we are telling that it is high, if we look at that span from 0 to 8.5 second, the maximum is here where we have taken the template. For the other cycles the maximum is not that high, but most of the cases they are above 0.9, but let us look at the last one. It has come much below the 0.9, it is probably just little above the 0.8 here. Okay. So, that threshold also can have some effect. Okay. So, that is the thing we understand, and let us proceed for that how we can do the synchronous averaging. Now, we perform the threshold, and first point is that we have taken the threshold starting from 0.8. Okay. We found that it seems to be a good value, and from there that what we have taken those points, we are interested in those points that where the cross correlation is more than the threshold. Okay. Now, I would request you to visualize the cross correlation graph. So, it looks like undulation and then high, and then again undulations are there. So, once we are taking a threshold, so above that threshold actually we would not get just one point, but all the points within this span. Okay. Within this span all the points would come. So, all those indexes would be stored here. Okay. Now, what we are doing, that we are taking that passing through that indices and to find out the length. Okay. That we have to do that synchronous averaging, and we need to make sure that while doing the averaging the values are defined. Okay. So, we are starting from 1 to length of the index minus 1. So, for each of these occurrence you take one bit is there, and we have to take that average of that length. And for that, as we are taking the average or the sum, first we would like to take those parts as a separate vectors, and then we will do the averaging. So, first we pick up those part. So, how we pick up that part? That we are taking from one index, okay, that index is minus n and index that x I plus n. Please keep in mind this n is the value of the half of the template. Okay. So, we need to keep that in mind, otherwise it will look like a bizarre piece of code, that this is the half of the length of the template. So, we are actually copying same as the length of the the template, that part of the signal, keeping that index where it is crossing the signal value, that means the bit location in mind, centering the bit location, we are taking that value. Okay. And while doing that, another thing we need to keep in mind, as we are taking both the side, some part is going towards the left, some part is going towards the right of that location I and D x I. So, the left part should not be less than 1, because if it is less than 1, then there would be an error, the program will crash, and same way it will program will crash if we try to pick up some value beyond the length of the vector. So, that also these two things we need to check, and in that way we pick up all the points or all those vectors, that how many copies of the signal we get, and in this process we may actually miss the last or the first bit if there is not sufficient number of points. Okay. So, that could be the penalty, but at least we would not have any crash in the program. And once we have all those that vectors, we now can take the mean. Now, this mean, it is not a single value, it is the mean of the vectors of two dimensional vectors, and so this itself would be a row vector. Okay. And that will give us the synchronized average value, that row. Okay. So, that is the way we have been successful in computing that synchronized average. Okay. That is the code. Now, let us proceed to see that how we get these values. So, here for 0.8 we are plotting that the noisy signal first at the top, here is the noisy signal, one cycle. Typically, we have taken the template, and below we are showing that synchronized average output. It looks so clean. Okay. And as it looks very near to the signal, we have taken this as a reference. Okay. You see that all the high frequency noise or the undulation due to that has gone. Okay. So, we take that as the reference signal for threshold equal to 0.8, and with respect to that, now we will judge that how the other thresholds will do. So, now what we do here, in the left hand side we are showing again the noisy ECG. We have shown it in a small way, so that we can see the other waveforms for different value of the threshold, and we can see them together in the same place. So, first we start with threshold 0.4, and with respect to the reference we get, it is 9.11 dB. So, the SNR is not that good. Now, what is the reason for that? If we look at the signals in all these cases, maybe here we can get some noise, but up to 0.8 all the cases they are very smooth. So, all of them they are successful in suppressing the noise, but what has gone here, it seems the shape of the signal has got distorted. Okay. How the shape has changed? If we look at this portion, that point Q, say here actually this is the Q, this is R, this is S, this is P, this is T. So, Q point if you look at, it has become very wide. Okay. What has happened that this peak, QRS peak has become also wide, okay, in this case, and T wave, look at that compared to the T wave in the original signal, it has become much higher. Okay. So, it has distorted to a good extent, and that is why SNR is so low. Okay. Now, threshold when we take 0.5, the situation has improved, but still all those problems are there. 0.6 again somewhat better, okay. 0.7 even better, 0.8 is the best, and 0.9 when we are taking, then we see that again the noise is reappearing. In fact, that if we can magnify the signal, you can get the feeling that 0.7 onward probably noise is probably trying to reappear kind of thing, and they are for sure visible in 0.9. Now, why this thing is happening? Okay. To understand that, we need to go back a little, we need to go back to the that place where we have that the cross correlation signal. So, in this place. Now, if I take a threshold say at 0.4, what will happen that here a number of points actually will appear above the threshold. It is not just one sample. For synchronized averaging would be successful if we have one sample, that means one interval we are taking. But in this case we will have actually multiple samples above the threshold. So, we are taking actually copies which are little disarrayed. Okay. So, number of copies we are taking. So, the effect of the summing up of them would be actually smearing that signal. Now, as we have more and more copies, suppression of the noise or averaging would be better, leading to better suppression of the noise, but at the same time because of the smearing of the signal, the width of the that peak should increase, it will become even more smooth. So, that is the challenge, and some of the peaks here, the noise peaks which are just above the threshold, that which are no alignment is there, that they will also come. So, some spurious peaks will come. So, that will distort the signal further. Now, as we move it up, this threshold, when we go above say at 0.9, what is happening? Say when we are going there, then some of the peaks, say this peak, this peak, this peak, probably this peak also, some of this peak would be missing. And as the peaks are missing, first of all that the averaging will suffer. So, the noise actually reappearing there, though the signal morphology is not changed in that case. So, there is a contradiction. If we take the threshold very high, then what will happen? We have insufficient averaging because the number of beats we could catch is less. The noise suppression would not be complete, and when we push it very low, then the spurious peaks are coming and they are disturbing the signal morphology, changing that. So, we need to take something in between. The ideal point would be that if we can get one copy of each cycle, okay, and 0.8 could actually be close to that. So, that is the way we have got actually with 0.8 the giving the base signal, and we have taken that reference, and we have used the PSNR or the in this case SNR actually to get that thing, to quantify that changes, that for 0.4 it is starting from 9. So, it has increased to 17.5 for 0.7 as a threshold, and when it going for threshold 0.9, it has a very slight increase. Okay. That means, the morphology has become better, but then noise is coming which is counterbalancing the gain. Okay. So, that is the thing we learn here, which is summarized at the end, that synchronous averaging, it is a very good technique to reduce the high frequency noise present in the signal, and as we change the threshold value from 0.4 to 0.6, the output becomes more and more smooth, but they are distorted. Okay. That means, low threshold it gives good noise suppression, but distorted signal. Threshold value again above 0.85, what we see that it gives undistorted waveform, but some high frequency noise are seems to be present, because the averaging is not complete, or there are less number of templates to take average. So, the best result is obtained at threshold 0.8, and with that we conclude this problem number 2 in the tutorial number 1. Thank you.